Integrals. Definite integrals. The definite integral refers to the net area of the plane region bounded by a continuous function f on the closed interval a, b. The integral of f of x, dx, from a to b, is equal to the limit as n approaches positive infinity of the summation from I equals 1 to n of f of x I star times delta x, provided that the limit exists. The numbers a and b are the lower and upper limits of integration, respectively. The following figure illustrates the concept of definite integrals. Consider the region bounded by a continuous function f and the x-axis on the closed interval a, b. The definite integral represents the difference between the area above the x-axis and the area below the x-axis, in other words, the net area, from x equals a to x equals b. A definite integral is the limit of the Riemann sum as the number of subintervals increases without bound. If f is continuous on the closed interval a, b, then f is integrable on a, b. An integrable function means that the integral of f of x, dx, from a to b, exists. In other words, if the limit exists, then f is integrable. A definite integral is a number, positive, negative, or zero. If f lies above, f of x is greater than 0, and or below, f of x is less than 0, the x-axis on a, b. The definite integral can be interpreted as the net area bounded by the graph of f and the x-axis from x equals a to x equals b. Consider again the following figure. Getting the definite integral of a continuous function f on the closed interval a, b denotes the net area of the plane region. The area above the x-axis is regarded as positive, while the area below the x-axis is regarded as negative. Meanwhile, if f is continuous and non-negative on a, b, the definite integral represents the area A of the plane region bounded by the graph of f and the x-axis from x equals a to x equals b. The definite integral in this case is non-negative, in other words, a is greater than or equal to 0. Consider the following figure. Getting the definite integral of a continuous and non-negative function f on the closed interval a, b denotes the area of the plane region bounded by f and the x-axis from x equals a to x equals b. Examples. Compute the definite integral of the indicated region assuming the n subintervals have equal length. And using the right endpoint xi of a subinterval. As the sample point xi star. Number 1. The region bounded by f of x equals x plus 1 and the x-axis from x equals 1 to x equals 4. Solution. Calculate the length of each subinterval. Use the right endpoint of a subinterval as the sample point xi star. Set up the definite integral. Afterwards, evaluate the definite integral. Write the integrals in terms of the limit definition. Substitute the right endpoint as the sample point and delta x equals 3 over n. Distribute the constant and the summation. Apply summation formulas. Simplify the quotients. Divide out the common factors and move the constant multiplier outside the limit. Evaluate the limit using a limit at infinity rule. Therefore, the integral of x plus 1 dx from 1 to 4 is equal to 21 over 2. Because f of x equals x plus 1 is non-negative on 1, 4, 21 over 2 corresponds to the area of the region under f on 1, 4. Number 2. The region, bounded by f of x equals x minus 3 and the x-axis from x equals 1 to x equals 6. Solution. Calculate the length of each subinterval. Use the right endpoint of a subinterval as the sample point xi star. Set up the definite integral. Afterwards, evaluate the definite integral. Write the integrals in terms of the limit definition. Substitute the right endpoint as the sample point and delta x equals 5 over n. Distribute the constant and the summation. Apply summation formulas. Simplify the quotients. Divide out the common factors and move the constant multiplier outside the limit. Evaluate the limit using a limit at infinity rule. Accordingly, the integral of x minus 3 dx from 1 to 6 is equal to 5 over 2. Because f of x equals x minus 3 is not non-negative on 1, 6, in other words, f also goes below the x-axis. 5 over 2 corresponds to the net area of the region bounded by f on 1, 6. Number 3. The region bounded by f of x equals 4 minus x squared over 3 and the x-axis from x equals 0 to x equals 4. Solution. Calculate the length of each subinterval. Use the right endpoint of a subinterval as the sample point xi*. Set up the definite integral. Afterwards, evaluate the definite integral. Write the integrals in terms of the limit definition. Substitute the right endpoint as the sample point and delta x equals 4 over n. Distribute the constant and the summation. Apply summation formulas. Simplify the quotients. Divide out the common factors and move the constant multiplier outside the limit. Evaluate the limit using a limit at infinity rule. Therefore, the integral of 4 minus x squared over 3 dx from 0 to 4 is equal to 80 over 9. Because f of x equals 4 minus by 2/3 is not non-negative on 0, 4, in other words, f also goes below the x-axis. 80 over 9 corresponds to the net area of the region bounded by f on 0, 4. Examples. Evaluate the definite integral. Using the limit definition where the subintervals have equal length. And the sample point xi* is the right endpoint on each subinterval. The integral of 2x, dx, from 0 to 2. Solution. Define the length of each subinterval. Set the right endpoint of a subinterval as the sample point xi*. Set up and evaluate the definite integral. Write the integrals in terms of the limit definition. Substitute the right endpoint as the sample point and delta x equals 2 over n. Apply summation formulas. Simplify the quotient. Divide out the common factors and move the constant multiplier outside the limit. Evaluate the limit using a limit at infinity rule. Hence, the integral of 2x dx from 0 to 2 is equal to 4. Number 2. The integral of quantity 1 minus x squared dx from -1 to 1. Solution. Define the length of each subinterval. Set the right endpoint of a subinterval as the sample point xi*. Set up and evaluate the definite integral. Write the integrals in terms of the limit definition. Substitute the right endpoint as the sample point and delta x equals 2 over n. Expand the square of binomial. Distribute the constant and the summation. Use summation formulas. Simplify the quotients. Divide out the common factors and move the constant multiplier outside the limit. Evaluate the limit using a limit at infinity rule. Thus, the integral of 1 minus x squared dx from -1 to 1 is equal to 4 over 3. Example: determine the integrability of f. Number 1. Answer: f is continuous on the closed interval 1 plus 5 pi over 6. Hence, f is integrable on the closed interval 1 plus 5 pi over 6. It means that the limit of the Riemann sum exists and the area under F is finite. In addition, F is integrable on any closed interval a, b, where F is continuous. Meanwhile, F is discontinuous at x equals -4 and -1. Consequently, F is not integrable on a closed interval a, b, containing -4 and -1. It means that the limit of the Riemann sum does not exist. For instance, F is not integrable on the closed interval -5, -3, and -3, 1. Indefinite integrals. The antiderivative f of a function f on an interval satisfies for all x in that interval. That is, the derivative of the antiderivative of a function leads to that function. The indefinite integral G is the family of all antiderivatives of f. Where each value of c correspond to an antiderivative of the same family. The symbol is called the integral sign. F of x is the integrand. Dx is the differential of the variable of integration x. And c is the constant of integration. The terms antiderivative and indefinite integrals can be used synonymously. An indefinite integral is a function or a family of antiderivatives f. While a definite integral is a number. Consider the following figure, which contains the graph of a family antiderivatives. An indefinite integral f of x plus c is a family of functions. The derivatives of these functions are the same because the derivative of the constants is equal to 0. An indefinite integral represents a function or mapping that computes on a closed interval a, b. The total area bounded by f. The total change given the rate of change f'. The following figure illustrates these concepts. The graph shows the curve of a function and its integral. The total area bounded by the blue curve on the given interval is the difference between the values of the integral at the end points of the interval. Meanwhile, the total change delta f, the blue curve has undergone, on the interval is the difference between the values of the integral at the end points of the interval. Integration is the process of finding the indefinite integral. Similarly, anti-differentiation is the process of finding the antiderivative. Integration and differentiation are inverse operations. In differentiation, differentiating a function leads to its derivative. Meanwhile, in anti-differentiation, integrating a function leads to an antiderivative. The original function can be thought of as the derivative of the antiderivative. While differentiation rules provide the derivative of a function, the reversed rules may be applied to find the antiderivative of a function. For instance, the derivative of a constant c is 0, while the antiderivative of 0 is an arbitrary constant. The derivative of a constant k times the independent variable leads to the constant, while the antiderivative of a constant k leads to the constant k times the variable of integration. A constant multiplier k can be taken outside of the derivative and integral signs and then proceed with differentiation and integration, respectively. Finally, differentiation and integration can be distributed over sum or difference operations. The table of antiderivatives is a list of some of the basic anti-differentiation rules. Examples. Find the indefinite integral of the following functions. Number 1. f of x equals the sine of x plus the cosine of x. Solution. Please refer to the anti-differentiation rules and the table of antiderivatives to be able to determine the indefinite integral. The indefinite integral of f of x is f of x equals the negative of the cosine of x plus the sine of x plus c. Where c is an arbitrary constant. The answer can be verified by getting its derivative, which must return the original function f of x equals the sine of x plus the cosine of x. Number 2. f of t equals 1 minus t squared plus t raised to negative 1/2. Solution. Determine the indefinite integral using the table of antiderivatives. Therefore, the indefinite integral is f of t equals t minus 1/3 of t cubed plus 2t raised to 1/2 plus c. To verify the answer, find the derivative of f of t and see if it returns f of t. Number 3. g of x equals 5 times the secant squared of x. Solution. The antiderivative of a constant times a function is the product of the constant and the antiderivative. While the antiderivative that leads to tangent of x, which is secant squared of x, is in the table, the antiderivative of tangent of x is not. What is the antiderivative of tangent of x? The antiderivative of tangent of x is not as straightforward as that of sine of x and cosine x. The antiderivative of tangent of x is the negative of natural logarithm of cosine of x. Because the derivative of by chain rule of differentiation is tangent of x. Number 4. f of x equals the negative of the quotient of the hyperbolic cosine of x and the square of the hyperbolic sine of x. Solution. Using hyperbolic identities, f can be written as the negative of hyperbolic cosecant of x times the hyperbolic cotangent of x. Using the table of antiderivatives, its antiderivative is f of x equals the hyperbolic cosecant of x plus c. Meanwhile, the derivative of f is the negative of hyperbolic cosecant of x times the hyperbolic cotangent of x, which is the same as the original function. Number 5. h of z equals 7 raised to z plus e to the z plus e to the 7. Solution. Based on the table of antiderivatives, the indefinite integral of h of z is h of z equals 7 raised to z all over the natural logarithm of 7 plus e to the z plus e to the 7 times x plus c. Meanwhile, the derivative of h of z is which is the same as the original function. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.